Okay, time for us to do more practice. And the more practice that we get, the more chances we have to make sure our skills are finally honed, ready for our upcoming exam. Let's get going. Now we see our cover sheet, very standard, and we know what to be ready for. And we see our 8 problems coming up. No worries. 2 hours, 8 problems, plenty of time. Plenty of time. And no big surprises. We still get our table of Laplace transforms. That's the only thing we should be counting on. Everything else we got to bring with us. So make sure there's plenty of room up there. Then you've got it all nicely organized. Okay, of course, we should put our name. And, well, we'll go by solutions, right? That's what we're going to put here, solutions. And away we go. Exciting. Let's try to beat 2 hours, right? Yeah, of course, of course. According to the FDA, caffeine decays exponentially and has a half-life of 5 hours. Somebody studying for Math 267 exam starts reviewing after drinking one 8 fluid ounce, and which has 316 milligrams of caffeine, can of Redline Extreme Energy Drink. And part A, write the initial value problem. Okay, so I'm going to be honest with you. They left out some details. And for example, when they say, write the initial value problem, write the initial value problem of what? They're not being very good here about what the initial value problem is. Now, okay, when we see initial value problem, we really are saying to ourselves, okay, they mean an ODE problem. And there's some clues here in context. Now, on a real exam, we'll be a lot more explicit, and we're not going to rely on you to go for context. We see this phrase right here in particular is really important. We're saying that caffeine decays exponentially. And so we should say, okay, so this is about some sort of exponential growth decay model. Now, and we're talking about the caffeine. Okay. So that says, when we look at these numbers, see there's an 8 fluid ounces and a 316 milligrams of caffeine. So this is the important number, 316, because that says how much caffeine there was initially in the drink. And of course, as with all things in math, we make some very simple assumptions. Here, I think the simple assumption is it's just one shot, All right, good. Got your buzz going. And you're ready to do some studying because you got all that caffeine in your system, right? Well, no, you don't need that. Okay, now that's an initial value, good. And maybe the other piece of information that we need is the half-life. Okay, so half-life of 5 hours. All right, now that is going to come into play somewhere. So let's figure out where it all fits in. So what it is that we're modeling is caffeine. And so we need to have some value. And so they didn't give us a variable name. And caffeine starts with C, but C is a very dangerous thing to throw in as a variable. Well, since we're doing, let's do A. And we'll have A of t equals the amount of caffeine at time t. Okay, so that we're all clear on what it is that we're doing. Good. And so this 316, that's our initial time. So that's our A0, because we do have an initial value. The fact that it's an exponential, as soon as you hear the word exponential, that tells you exactly the differential equation that's involved. We don't even have to think about it. So our differential equation says that the rate of growth, that's A prime, is proportional to the current amount that there is. Now, because it's a decay, we might as well go ahead and say it's a negative value. And either you'll solve for k and it'll come out negative, or you won't solve for k and it will come out positive. So that's our basic formula. And now there's the question. What is K? And it's not so clear, do they expect K in part A? But if you read ahead, which, that's okay, it says find the solution, that might influence it. But the important thing here is that when we talk about our K, that's going to be coming from our half-life. Now, that doesn't mean our half-life is exactly equal to K. What it means is our half-life determines K. So, let's jump ahead and let's figure out how we're going to actually figure this out. Okay. Well, as I say, let's see what we can do. Now, if you have this should be automatic. In other words, when I say automatic, this is such a very fundamental model that we don't even have to go through the derivation of it. Now, if you wanted to. And if you did, you would do this as a separable differential equation. This is almost like day 1 or day 2 that we could solve this in our class. But what we know is that we have that our amount of caffeine at time t is equal to our initial amount, let's call it A0, and e to the minus kt. All right, now here's what we do. How does the half-life fit in? Well, what we have is that at time 5, we are half of our initial amount. So that's our A0, e to the minus k times 5. All right, and you'll notice the k vanishes. So that's why the value for k doesn't depend on your initial amount. The initial amount doesn't enter into the computation. It depends on the half-life, and in particular how long it takes to get there. Well, okay, take the log of both sides. Now, log of a half is equal to, well, here it'd be minus 5k. Now, there's a trick here. You might say, well, that's negative. Isn't that positive? That's weird. I thought k was supposed to be positive. The log of a half is the same as minus log 2. Well, minus minus makes plus. So, lo and behold, we get that k is 1/5 natural log 2. All right, so we are now ready to answer, what is our initial value problem? It is, we have a prime is equal to minus 1/5 natural log 2 times a, and a of 0 equals 316. And there we go. That's it. That wasn't so bad. Now for part B, we actually did most of the work for part B and part A. Part B says, well, what's the solution? Well, we actually have the solution here. We just say, well, we need to know A0. Well, we know that. We need to know K. Well, we know that. So we don't have to put a lot of thought into it. And we do have to write it down. So we get our solution. The amount of caffeine at time t is 316, our time 0. Then it's going to be e to the minus k. Well, that's minus k right there. So minus 1/5 log 2, whoops. Yeah, no, we're fine. Times t. Okay. Well, that was pretty quick. Now, for part C, how much caffeine is still in the system after a 36-hour session? Now, before we answer this question, I just want to point out, we do not endorse 36-hour study sessions for any class. It's not going to be very effective. Rather, it's better to spread a little bit of studying over, many sessions. So 20, 30 minutes, take a break, go outside if you can, if the weather's nice, or, talk to somebody, walk up and down the hallway. Give your mind a chance to rest, because you don't want to show up at the exam and fall asleep during the exam. I've seen students do it. It's a very bold strategy, but it usually doesn't pay off very well. So again, don't try to overstudy. It's not worth it. All right, but the answer, how much caffeine is still in the system after a 36-hour session, you plug in 36, because that's what we have. That's what A of t is modeling. So it's A of 36 would be 316 times e to the minus 1/5 log 2 times 36. And we can even be more precise. We can say it's milligrams. Because if you go back to our initial conditions, everything is being measured in milligrams. So there we go. That's it. See? Wonderful. Once you have part A, wow, the rest of it just flows. Smooth like butter. Maybe they should say smooth like a differential equation problem. Maybe someday they will. All right. Solve the ODE with an initial value. So the ODE, that's the differential equation. Initial value is here. So xy prime equals y plus 2y squared e to the x. And y of 1 equals 1. All right. Well, what's happening here? Now, it kind of feels linear. And in particular, we could start by saying, well, this is, we can write it as xy prime minus y is equal to 2 e to the x y squared. Now, here's the thing. If we covered up that y squared, we'd be like, perfect, linear. We can do this. No problems, no problems. But there's a y squared. So we're like, oh, problem. How do we handle this? Now, this comes back to something called the Bernoulli equation. All right, so let's just recall what Bernoulli equations are. It says the following. It says if you have y prime plus p of x y equals q of x y to the power n, that's the setting. So without that y to the n, it's a linear first order equation, but then you add this y to n. Now, n could be any number we want. In our case, n equals 2. Then the idea is do a substitution, and the substitution, it seems a little bit strange at first, and what it is you're going to let v be y to the power 1 minus n. That's where we're going to go. All right. Well, that's the idea. Now, all right, so what's going on with that substitution? Well, let's actually figure out what the substitution would be here. So in our case, we say, all right, our substitution that we want to be making is going to be y to the power 1 minus 2. Well, that means we're going to make v be y to the minus 1. Okay. Or v equals 1 over y. Now, what's v prime? Well, what's the derivative of 1 over y? The answer is minus 1 over y squared. All right. So, what happens? Oh, whoops. I almost told a lie here. What did I forget? Wait, what did he forget? Well, minus 1 over y squared, y prime. That's what I forgot. So notice what happens. And this is the secret of Bernoulli, is what you really should do is divide everything by this y to the power n. So what you have is you have x y prime over y squared minus 1 over y equals 2 e to the x. And this 2 e to the x doesn't involve y at all. And this 1 over y, that's the substitution. And this part will almost be the v prime, except possibly with a small sign issue. But a small sign issue, to be sure. Okay, so what do we come up with? Well, y prime over y squared is going to be become minus v prime. Okay, that's not so bad. We can handle that. And so we have the following. We get minus v prime here, minus v equals 2 e to the x. Or we can say, hey, this is v prime plus v is equal to 2 e to the x with a minus in front. Okay, great. Good, good. And now we're in linear first order. So what do? Well, okay, we put on our linear first order hat. Oops. I forgot something. Let me cross this off. It's okay to make mistakes. You just have to correct them. Do you see what I forgot? I forgot my x. I'm sorry, x. My apologies to you. Okay, so there is a minus. Don't forget the x. So minus x v prime minus v equals 2e to the x. Okay, whew. Good. This x was feeling left out. All right, now what do we want? Well, if it's linear, which will always happen, Bernoulli will transform into linear. You want to make this coefficient 1. So divide through by minus x. And so we have v prime plus 1 over x times v is equal to, and here we'll have minus 2 over x e to the x. And now the question becomes, what's the integrating factor? Now you might say, hey, if I spot the integrating factor without going through this process, is that okay? Yeah, sure it is. But it's good to know the process. So the trick is, once it's in the right form, you need to have a 1 in front of the v prime. Then you take what's in front of the v, including the sign, but that's okay, it's a plus this time, and we're going to integrate that. And in particular, we're going to have our integrating factor, which I'll abbreviate IF, is going to be e to the integral of 1 over x dx. Well, that's e to the natural log x. We don't need a plus c at this stage, which is x. So that's what our integrating factor is. So now we're going to multiply through by x. And now you'll see why I said, oh, yeah, that's why Steve said, hey, if you see it, it's okay. But what do we have? We have x v prime plus v is minus 2 e to the x. And the left-hand side, guarantee that if you've done this right, it's got to be a derivative. And it's got to be the derivative of your integrating factor times your function. Okay, so the derivative of x times v is minus 2 e to the x. And that says, hey, we can integrate that left-hand side pretty easily. And so we just do that. And then we just have to figure out the integral of the right-hand side. But in our case, good news, that's something that we can integrate. So we have x times v is equal to integral of minus 2 e to the x minus 2 e to the x plus, of course, some constant c. Now, do you remember what v was? V is 1 over y. So we have, if we do our substitution back, x over y is minus 2 e to the x plus some constant c. Okay, well, we're almost there. Almost there. So let's come back over here, because we have a little bit of space. You know, use your real estate, right? So how do we solve for y? Well, we can flip both sides, because there's only one y, so if we flip both sides, that will move the y up, and then we can multiply through by x. Now, the other thing we have to do is remember, it's easy to forget if it's not on the screen, it's an initial value problem. So we need to take into account our initial value. So we can actually do that now. you can solve for the initial value at any time after you've done the integration. And so if you're like, well, it seems like it might be easier to solve for it now, then solve for it. So plugging in our initial values, well, what we have, we were told y of 1 equals 1. That means both x and y equals 1. We get that 1 is equal to minus 2e plus some constant c. All right, well, that's fine. That says that c is 1 plus 2 times e. Okay, great. So we have x over y is equal to minus 2 e to the x plus 1 plus 2e. Flip both sides, y over x. Well, if you flip the other side, 1 over, you flip the whole thing. You don't flip it one term at a time. You flip everything. You know, it's like you're turning the, you put the spatula in under the whole thing, and whoo, the whole thing flips over. And to get y by itself, the last step, multiply through by x, and we get that y is equal to x all over minus 2 e to the x plus 1 plus 2e. And there we go. There we go. That's not so bad. That's not so bad at all. I mean, you got to work a little bit, but you always have to work a little bit, right? And, well, there we go. There we go. Good. Good. All right, well, that's number 2. A linear first order. We should be ready because we haven't seen enough of them on exams. The only thing that makes it a little bit of a wrinkle is, of course, the Bernoulli. It may or may not be a Bernoulli problem, but be ready for that. Be ready for it. All right. That brings us to number 3. An object with the mass of 1 slug is attached both to a vertically suspended spring that it stretches 4 feet and to a dashpot that provides 8 pounds of resistance for every foot per second of velocity. Whew. Okay, there's lots of weird words, especially if you're someone like me. I never really took physics after, I think I was a junior in high school, and this was really back in the old days, long time ago. I'm not going to say how long ago, because let's just say a long, long time ago. It's been a while. And so you see words like slugs and dashpots and like, wow, what are all these things going on here? Okay, so we're going to talk about that. And then there's a little bit more. It says, if the weight is pulled down 1 foot below its static equilibrium position and then released from rest at time t equals 0, find its position function x of t. Okay, so there's a couple of things that jump out to us. Now, the first thing that I want to point to is spring. It's like, okay, this is a spring problem. And so the good news about spring problems are they're set up in a nice way. So what we have is we have something x double prime plus something x prime plus something x is equal to something. So we have these 4 potential boxes to fill in. And I want to talk about what these boxes are, because this is not just do the problem. This is hey, let's review a little bit here, because I really want us to nail this. I'm just like, boom, it's not, I know how this works. I'm good. Now, the first box is great. And it should be pointed out that every one of these 4 things is all about a force. The first box here is about your mass. And so if you're trying to figure out what goes in front of the x double prime, look for the word mass. Hey, I see a mass. 1. Perfect. Now, the x prime term, what goes there? Now this one is a little bit different. It talks about a dashpot, and But really this is the same as your damper. So you could say damper / dashpot. So the idea here is you have a spring, and then you have your mass. So here's your mass. And then think about it as there's this rod here that goes into a device, and this device is filled with some sort of material. Water is a great example, some sort of fluid. And you'll see what happens is as you push, you'll get resistance. So the more you try to push, the more it resists. But it doesn't say, okay, if I start higher versus starting lower, it doesn't change. The thing that matters is your velocity. So the damper or dashpot, that's what goes into that part. It's coming into saying, okay, your resistance, the force coming from resistance of velocity. Okay, so we're looking for anything that's talking about the damper / dashpot. Okay, and here, a dashpot provides 8 pounds of resistance for every foot-pound per second of velocity. So this here, that 8 is what goes there. Okay. Now, the next box. Ooh, this is a fun box. This box here is Hooke's law. Okay, so we gotta make sure we understand what Hooke's law says. Now, Hooke's law says if you have a spring, and I feel bad I didn't grab a spring. Well, you don't have to bring a spring to the exam. You just have to be ready to think about it. Hooke's law says that the amount of force that an object, the amount of force pulling is proportional to how far you've pulled. So in other words, the further you stretch a spring, the higher the amount of force you have to do that. Now, the other thing, of course, is that the force is pulling the spring back to equilibrium. So what you end up with is this idea, Hooke's law, which says that force is minus kx. Okay, so how does this all fit in? Now, here's where it comes into play. So our force, okay, where do we find it? Okay, we got to be a little bit careful here. So the spring, Hooke's law is attached to the spring. And now what we've done is we have a object, and that's pulled it down. And it stretches 4 feet. Okay, so what we have is our force is minus k times 4. Now, how do you find force? Well, force is mass times acceleration. Okay. Now, what's our mass? 1 slug. Okay, so that's our mass. What's our acceleration? Well, it should be 32. And 32 feet per second per second. That's gravity. So in other words, that if you just think about the force, that if you just have this mass, what would it be? And that's what you'd end up with. And of course, we would should be pulling it down. And so what's our spring constant turn out to be? And it's 8. Okay. Oftentimes they'll just say your spring constant, which is such and such a number. All right. Great. Okay. So that's good. Good. Now, there's one more box. And what's the last box? By the way, I will say, sometimes they just say, with spring constant, this. And you're good to go. The last box, these are your external forces. And in other words, maybe there's some sort of mechanism attached to this object that's also driving it. And the question is there any external force? And the answer is no. So 0. All right. Good. So there's our setup. Okay, now that's the differential equation. We also have to talk about our initial values. So we have our x double prime plus 8x prime plus 8x equals 0. We have our, what is x of 0, what is x prime of 0. So now we start with the second part. If the weight is pulled down 1 foot below its static equilibrium position. So there's currently the weight is just neutral. We're pulling it down. Now here, it doesn't tell us, does that, being below, is that positive or negative? It's not clear from context because it can be either. Now that's one of the fun things about physics is you get to assign orientations. Let's assume that since below, we'll think about as a negative direction, it's -1. They can't mark us down if we made that assumption because it's a valid assumption. And then it says released from rest. What does that mean? Well, it means that you pulled it and then you just let it go. In other words, there's no initial velocity. So x prime of 0 equals 0. All right, good. That's our equation. So we just have to solve that equation. And now our goal is to find our function x of t. Okay, so all of this paragraph becomes this. This is a part of learning to translate. And that's an important part. In other words, it's sort of saying, how do you treat the world around us and make it think about it in a mathematical way? So we are ready to begin. So where do we begin? Well, it's a constant coefficient, linear, homogeneous differential equation. Like, this is beautiful. We want these kinds of equations on exams. Not that we necessarily have to pray for these things, but it's like, please give us something with constant coefficients, linear, homogeneous, because they're nice. And they are. They really are truly nice. All right, so here we go. First thing is, we translate this into a polynomial. R squared plus 8r plus 8 equals 0. And now what we need to do is find the roots. Well, if we can, maybe we can't. I don't know. It's not so clear. Now, we can do it by quadratic formula, or we could do it by some sort of completing the square. And if we did it by completing the square, let's see, what would we have here? Or does it factor nicely? Let's see, are there two numbers that multiply together to give 8 and add together to give 8? Not that I know of. Well, okay, suppose you did completing the square. What would you need to add to this part, r squared plus 8r plus what? Well, divide 8 by 2, that's 4, squared is 16. Then we have to subtract 8 equals 0, right? Because 16 minus 8 gives us 8. And that says, this first part is r plus 4 squared. And then this other part, this minus 8, comes over to 8. So r plus 4 equals plus or minus the square root of 8. Well, that's 2 square roots of 2. Or you can get r equals negative 4 plus minus 2 times square root of 2. Okay, well, these are going to be numbers. In some sense, these are actually nice numbers. Because what do we see? They're real roots, and they're distinct roots. Now, in terms of the spring mass system here, that means that this has been overdamped. And there's not going to be, the spring will not be very springy. That says the damper is so effective at doing its dampening thing that it's going to just slowly go back to equilibrium. So, in other words, after you push it down, it's not going to go like this. After you push it down, it's going to go like this. Okay. And back to where you began. All right. Well, so we have our two roots. So it says our solution, x of t, is some constant a, e to the minus 4 plus 2 root 2 times t, plus some other constant b, e to the minus 4 minus 2 root 2 times t. All right, well, great. And now we have to do our initial conditions. We'll need x prime. So x prime of t, minus 4 plus 2 root 2, a, e to the minus 4 plus 2 root 2 t, plus b, minus 4 minus 2 root 2 times, e to the minus 4 minus 2 root 2 t. I don't know why I wrote this times a and this b times that. That's all right. Everything's there. Now, plugging in our initial conditions, what do we have? Well, we have that x of 0, that's a plus b. And we're told that equals negative 1. And x prime is 0, well, that's minus 4 plus 2 root 2 times a plus minus 4 minus 2 root 2 times b, and that has to equal 0. Okay, 2 equations and 2 unknowns. Okay, what do we do? What do we do? Well, the good news is we don't have to think too much, right? And so what we can do is we can do all sorts of things. One example is I can say, okay, look, this says that b is minus 1 minus a, all right? Because I can just solve for b. And so we can say, okay, minus 4 plus 2 root 2 times a plus minus 4 minus 2 root 2 times minus 1 minus a equals 0. Now, there's so many negatives in here that you can say, okay, pull out a negative, everything's positive. And so what do we have? We have minus 4a plus 2 root 2 times a. And then here we have plus 4 plus 2 root 2 plus 4a plus 2 root 2a. And all that equals 0. And hopefully we can get a little bit of cancellation here. And we do get some. The minus 4a and the plus 4a, those cancel. So that's the good news. And what do we have? Well, we get 2 root 2, so that's 4 root 2 times a equals, move that to the other side, minus 4 minus 2 root 2. And now we just divide through by 4. So a equals minus 4 minus 2 root 2 over 4 root 2. Well, here's when we start pulling out some fun things. So notice this is minus 1 over root 2. And here you'll get minus 1 over 2, right? Because the second term cancels. Now, minus 1 over 2, that's the same as root 2 over 2. So this is the same as minus root 2 plus 1 over 2. All right, so that's A. What about B? Well, B is minus 1 minus A. And so that would be what? Well, minus 1 plus root 2 plus 1 over 2, which becomes, the only thing that happens, think of this as minus 2 over 2. So this becomes root 2 minus 1 over 2. And there we have it. There we have it. Wow. Good. And the only thing that's not good is we've run out of space on our page to write the answer. And of course, I do have to be honest with you. I look at this and say, boy, I really hope we haven't missed anything, because that's such a strange answer with root 2's floating around. But sometimes when they write these practice problems, they're just sort of like, well, it's an answer, right? We can just clean it up in post-production. On an exam, our answers would be much nicer. Okay, so let's just write our final answer nice and clean. So x of t is equal to a, and a is here, so that's minus root 2 plus 1 over 2. Okay, so there's the a. Then it's e to the minus 4 plus 2 root 2 times t. Then we have b, and b is root 2 minus 1 over 2. So we have plus root 2 minus 1 over 2. And then that's going to be e to the minus 4 minus 2 root 2 times t. Exactly what we would have thought. No. That is not exactly what we would have thought. But, sometimes that's just how it works out. You just got to be patient with it. And that's all right. It's okay. It's okay. Well, fun problem. Realistically, the numbers, the ideas are good. Realistically, the numbers would not be what you'd see on an exam, because we would give something, I would hope, a little bit more reasonable. I hope. All right. Well, moving right along. Number 4. Solve the following system with the initial conditions: x of 1 equals 0, y of 1 equals 1. Okay, so we have x prime equals minus 5x minus y prime equals 4x minus y. All right. Well, again, I like to write this as a system. I like to write it in terms of a nice matrix form. So I'm going to write it as x. Now you can't tell, but this is actually a bold x. So this is not the same x as here. It's a bold x. So I'm thinking of this as sort of a vector. So x prime, and gather the coefficients: minus 5, minus 1, 4, minus 1 times x. So really, I'm going to be using the eigenvalue method to solve this problem. I like eigenvalues. Now, it doesn't say you have to use the eigenvalue method, so we could do some other approach. But I think the eigenvalue method is a fairly reasonable way to approach a problem like this. All right, so what do we need to do? Well, we need to find the eigenvalues. So this part here, this is our a. So we're going to set 0 equal to the determinant of a minus lambda I. Okay, so that would be the determinant of minus 5 minus lambda minus 1, 4 minus 1 minus lambda. All right, so we take, diagonal, subtract. So minus 5 minus lambda minus 1 minus lambda, subtract 4 times negative 1. The nice thing is everything here is being negative, makes it all the same as if everything were positive. So you get lambda squared, and then you have 5 lambda and lambda. That makes 6 lambda. Then you have 5, and here you have plus 4 more. So that makes plus 9. So lambda squared plus 6 lambda plus 9. All right, well, that's not so bad. I don't think it's bad, is it? No, it's not bad. Okay, and all right, what do we do? Well, we set this equal to 0, which means solve for roots. Now, the last one we did completing the square. Let's do a quadratic formula just so we can mix things up. See our different approaches. So we set that equal to 0. I don't see any way Does this factor nicely? Oh, maybe it does. Why do we need to do anything fancy if a non-fancy thing works? Because what do we need? Two numbers that multiply together to give 9, but add together to give 6. Yeah, that actually factors pretty nicely. Lambda plus 3 squared. Okay, so what does that say? So that says our eigenvalues are going to be -3 and -3. Okay, good. We have repeated eigenvalues. Now, you should be suspicious that if you see repeated eigenvalues, you probably are going to have to do something about not enough eigenvectors, especially if it's 2 by 2. If it's 2 by 2, if you see a repeated eigenvalue, and the problem is not super boring, yeah, you're going to have to do something about missing eigenvectors. Now, let's find out, is that happening here? Okay, so we're going to look at this matrix A minus lambda I. Now, in our case, that becomes A plus 3i. So that's minus 3 is plus. And so that is the matrix. That would become -2, -1, and 4, 2. Okay, so first thing is the eigenvector computation. And we say, okay, well, we need to find some vector, AB, that when we multiply, we get 0, 0. Now, if you think about what's going on here, you really have two equations. -2a minus b equals 0, 4a plus 2b equals 0. And if you look at those two equations, well, let's actually look at them. We have the technology, Steve. Yeah, we do. -2a minus b equals 0, and 4a plus 2b equals 0. What do you notice about these two equations? They're really the same equation. The only difference between these two equations is a factor of -2, which means you can throw out one of the equations. And that's why you have a chance. So you should have a redundancy. And we come to our conclusion that if we have an eigenvector, b has to be -2a. So our eigenvector, well, looks like a minus 2a, or if you like, a1 -2. So here's our eigenvector. This will be important. This is going to be part of our answer. Okay. Well, good news. We found an eigenvector. Bad news. We only found one. And when we say we only found one, every other eigenvector looks like this up to some multiple. So you might say, oh, what about 2, -4? Well, it's the same thing because it's some multiple. We don't care about multiples. We already knew that would happen. When we're looking for some things, we want something linearly independent. So we say, ooh, all right, so what do we do? What do we do? And the answer is we do our generalized eigenvectors, right? And that's what it was referred to. So you have your generalized eigenvector. And how does this work? Well, you're going to take this same matrix. And the key thing is this is the matrix A minus lambda I. And it's really important that it's A minus lambda I, not lambda I minus A. It has to be this matrix, A minus lambda I. So it's the same matrix. And now what we're going to do is we're going to multiply this by some vector CD. And we want not 0, 0, but we want this 1 minus 2. All right, so that's the key here, that this becomes our new. It's our new 0, 0. Okay, so what does this tell us? All right, well, if we look at the equations, minus 2c plus d needs to equal 1. And then the second, I'm just minus 2c plus d equals 1. And here we get 4c plus 2d has to equal minus 2. And Did I copy something down wrong? I did. I forgot there's a minus here. See? Because I was going to say, aha, they're the same equation, but they weren't because I had a typo. And that's okay. If you're like, wait a second, something was supposed to happen. Oops. I see. Typo. Lots of small checks. Add in those small checks and you can catch errors. And the sooner you catch errors, like the more you're like, yeah, good job, you. You're doing great. Keep finding those errors. Okay, so, but now we say, hey, these are really the same equations. And so we say, aha, as we anticipated, which you should. You should. But now what's the thing? Now we look at this and say, well, we just need one solution. Any solution works. So I just have to find some choice for C and some choice for D, where that's true. And if I do that, I've won. Okay. Can you see one? Well, there's actually infinitely many. So that's the good news. So the good news is you only have to find one. And here's one that works. So one solution. And they're among many. Again, we know there's going to be lots of them. Is C equals 0 and D equals minus 1, which gives us 0, minus 1. Okay, so this is our other important piece. Now, what do we do with these? And here's the idea. Once you have these, what you've really been doing is you've been constructing solutions. See, our eigenvector, eigenvalue pairs are solutions. So we know that one solution is, and I'll choose say, look, there's some constant A, and then it's e to the eigenvalue times eigenvector, 1 minus 2. And now the second solution, here's where we have to do the generalized eigenvector. So it's still e to the minus eigenvalue t, but we do our bump. So there's t times 1 minus 2 plus this piece downstairs that we just computed. So 0 minus 1. All right, so there's our solutions. Okay, so that's what x looks like. Now, this is an initial value, right? When we plug in 1, we get 0. And when we plug in 1 here, we get 1. Now, I'm just going to pause here and just be like, okay, sorry. Because I know what's coming. And it's not going to be fun. There's a small thing here. 1 is not a wonderful initial condition. We're going to get lots of e's floating around. So we'll deal with it. We'll deal with it. That's okay. But let's go. So what we have is the following. Now we plug in at time 1. So at time equals 1, we have that x of 1. Well, it's our little x of 1, which is 0, and our little y of 1, which is 1. Okay. And that's going to be equal to a e to the minus 3 times 1 minus 2, and b e to the minus 3, because I'm plugging in t equals 1, and here plug in t equals 1, and we're going to get 1 plus 0, which is 1, and minus 2 minus 1, so minus 3. All right. Okay, so this leads us to 2 equations and 2 unknowns. And we have, well, the first one, it says a e to the minus 3 plus b e to the minus 3 equals 0. All right, so 0, the top part. Notice the e to the minus 3's are the same. So it really says, hey, a plus b equals 0, which really says, hey, A is minus B. All right, great. So that's something. So our A and our B's are not so far off. Okay, a little something. There's a second equation. So what does that equation say? It says minus 2A e to the minus 3 minus 3B e to the minus 3 equals 1. But remember, we said A equals minus B. So if we put that in, A equals negative B, what does that say? Well, that would say 2B, or is it not 2B? No, it's 2B. Okay, e to the minus 3 minus 3B e to the minus 3 equals 1. And, okay, so we subtract, and we end up with minus B e to the minus 3 equals 1, because there's 2B minus 3B. Well, I made some small mistakes, and so I want to fix myself now. You know, as the saying goes, you know, check yourself before you wreck yourself. All right, let's solve for B again. So what is B? I'm going to move the negative across, and this e to the negative 3 will come across as well. How will it come across? Well, you can divide by e to the negative 3, which is the same as multiplying by e to the positive 3. So what we end up with is B is minus e to the positive 3. And A, remember, is the opposite sign of that. So A is e to the positive 3. Now you can check it up here. E to the 3 times e to the minus 3 makes 1. Okay, so really what we have is 1 times this factor minus 1 times that factor. And 1 minus 1 is 0. Minus 2 plus 3 is 1. So that's what we want. All right, good. Good. So we're out of space. That's okay. We're not out of paper. There's always more paper. Always more paper. Okay, so let's write what we have here. So we have now our solution. X is equal to A, and A is e to the 3. So that's e to the 3, e to the minus 3t, 1 minus 2. And B is minus e to the 3. So minus e to the 3, e to the minus 3t times t 1 minus 2 plus 0 minus 1. All right, now our goal is to clean it up. We're not quite to our final answer, but we're going to talk about it, and we're almost to our final answer, and that's the good news. Okay, so what are some things we should do to clean it up? Well, notice this part right here, e to the 3 times e to the minus 3t. We can actually put that as one piece. So think of this as e to the minus 3t plus 3, which is the same as e to the 3t minus, e to the minus 3 times t minus 1. So this part right here, same thing, e to the minus 3 t minus 1. Now, big surprise that we see t minus 1, because we know time equals 1 is when we were interested in that time equals 1, we had nice numbers. So the exponentials should have basically become nice. The only way to do that is have e to the 0. The other thing, while we're at it, and we're here, this piece, we can write this as t plus 0 and minus 2t minus 1. So I'm just t times 1 plus 0 minus 2 times t plus minus 1. So what does this become? Well, if we factor out the e to the minus 3 times t minus 1, then what we have is the 1 minus 2 subtract this. And, well, we'll do that a little bit slowly. We won't try to do it all in our heads at once. It's always dangerous to try to do everything in your head at once. I'm proof of that. you've seen already, I've made some small errors. But the good news is we can check for our errors and we can fix them. Okay, so we get 1 subtract t, so 1 minus t. And then here we have minus 2 minus minus 2t, and then minus minus 1. So that becomes minus 1 and plus 2t, which becomes 1 minus t e to the minus 3t minus 1, and minus 1 plus 2t e to the minus 3t minus 1. All right. Now, why are we doing all of this? Just as a reminder, the issue here is it said solve for x and y. But notice we put things into vector form, but that's something that we introduced. That's not part of the problem. That was something that we said, hey, for convenience, we're going to think about this. So what we have to do is we said we have to unwrap. And, well, the key here is that the first entry is what we were calling our x, and the second entry is what we were calling our y. And so we now are ready. We can say, aha, x of t is 1 minus t e to the minus 3 t minus 1, and y of t minus 1 plus 2t e to the minus 3 t minus 1. And there we go. Beautiful, beautiful answer. Well, not the most beautiful answer, to be honest. But, you know, it's an answer. It's an answer. So we got there. All right. Well, good. And if we were paranoid, we could always check into there. But I feel pretty good about our work. So we'll just keep going because we're only halfway through. I know, it feels like we just started, but got to keep going. Through. So number 5. All right. For the system of the ODEs, you have x prime equals ax. A is minus 1 minus 2 minus a half 1. And x of 0 is 2, 2. And find the exponential matrix e to the at and use it to find the particular solution x of t. All right. No problems. We can do that. We have the technology, right? Yeah, we do. Okay, so what do we do? Well, now when you think of the exponential matrix e to the at, really you can say this is a fundamental matrix. And, well, it has the word fun in it, right? So we should be expecting some fun things to happen. We'll find out. We'll find out. All right, so fundamental matrix. So oftentimes start by looking at eigenvalues. So eigenvalues will give you a good idea of where to go. Okay, so we're going to set 0 equal a minus lambda I. So we're taking the determinant minus 1 minus lambda minus 2 minus a half 1 minus lambda. So that's minus 1 minus lambda, 1 minus lambda, subtract negative a half times minus 2. So let's see, we have minus lambda times minus lambda, which is lambda squared. You get a plus lambda and a minus lambda, which cancels. Then you have a minus 1, subtract minus 1. So you get lambda squared minus 2. And you set that equal to 0. So what does that say? Well, it says lambda squared equals 2. All right. Well, what does that say? Well, that says your eigenvalues are plus or minus square root of 2. Oh, so yeah, this exam has a lot of square root of 2's in it. And I'm just going to pause here. Don't expect that the real exam is going to have numbers that don't work out so weird. You know, the real exam, the numbers are going to be much nicer. At least I'm going to try my best. Fingers crossed I succeed in campaigning to get nicer numbers. Okay, well, here we go. So, why did we do this? Well, once we have the eigenvalues, that tells us sort of where to go. If our eigenvalues had been 0, we would say, oh, super easy, e to the at, you do I plus a times t, and you're basically done if it's 2 by 2. If the eigenvalues had been the same, you can tweak that a little bit. There's a little bit of work that goes into it. If you were wondering what I mean, you can look at the old practice exams, and there's an example of what you do. If the eigenvalues are distinct, it's probably going to be a lot easier for you not to use the definition of e to the at in terms of adding up infinitely many things, but rather finding the fundamental matrix and then turning that into the fundamental matrix that corresponds to e to the at. And so that's the case we find ourselves in. The thing that's going to make this a little bit time-consuming is not the ideas. The ideas are not so bad. It's that we have the square roots floating around. So it's going to make the numbers just a little bit less pleasant to work with. But don't let that turn you off. Just be like, okay, it is what it is. That's how you should be going on this. Yeah, well, it is what it is. Okay, good attitude to have. I like your attitude. Keep that attitude. It'll help you. So let's begin. We got to find our solution. So we'll start with lambda equals plus the square root of 2. And what do we have? Well, we're going to look at a minus lambda I. So we have our minus 1 minus root 2, minus 2, minus a half, and 1 minus root 2. Okay, so there's our a minus lambda I, and we're going to multiply it by some vector ab, and we're going to get 0, 0. Now, what's not so clear, but is still nonetheless true, is that there's redundancy. So what you really have is you have two equations. And we know that there's redundancy, so we're going to use that to our advantage. So our two equations are minus 1 minus root 2 times a minus 2b equals 0, and minus a half times a plus 1 minus root 2 times b equals 0. This bottom equation, notice you can move the minus a half a across and double and come to the conclusion that a is equal to 2 minus 2 root 2 times b. Okay, so I moved the minus a half a across and I doubled. So that says, oh, my vector AB, I can think of that as 2 minus 2 root 2 and as 1. Then I pulled out a factor of b. So here's my eigenvector. All right, now that's lambda equals plus square root of 2. Lambda equals minus square root of 2. Well, probably not going to surprise you. Very similar. And we're going to get minus 1 plus square root of 2, minus 2, minus a half, 1 plus square root of 2, a, b equals 0, 0. And we're trying to solve for ab again. And I'm just going to focus on that bottom equation. Minus a half times a plus 1 plus root 2 times b equals 0. So that says that a, again, move the half a across and double, is equal to 2 plus 2 root 2 times b. And so we get our vector ab looks like 2 plus 2 root 2, 1 b. All right. Now, how does this help us? Well, what we end up with is now that we have our eigenvalues, eigenvectors, we get that our general solution looks like x of t is some constant, c, e to the square root of 2t, so the eigenvalue times t, times eigenvector, plus some constant d, e to the minus root 2 times t times the eigenvector. Great. Now, we've built up a collection of solutions. The next thing to do is to say, hey, what is our fundamental matrix? And what we do is we just say, okay, we slide our solutions in. So we're going to get 2 minus 2 root 2 e to the root 2 times t and e to the root 2 times t, and 2 plus 2 root 2 times e to the minus root 2t and e to the minus root 2 times t. Okay, so that's our nice fundamental matrix. So again, this goes down here, and just so we follow along, this other part goes into there. All right. Now, we're not done, and we're already out of space. So, on to the next page. Well, okay. All right, on to the next page. Okay. Let me grab a blank piece of paper here. All right. So, what's our key? Well, our key here, and this is where we're moving with this, is we have that e to the at is equal to phi of t times phi of 0 inverse. So we have phi of t. So we'll just copy that down again. Phi of t is this matrix, 2 minus 2 root 2 e to the root 2 times t, e to the root 2 times t, and then 2 plus 2 root 2 e to the minus root 2 times t, e to the minus root 2 times t. So we need to clean that up. Well, we need to find phi of 0, then we need to find phi 0 inverse. Now the nice thing is phi of 0 is super easy. All these eta stuff disappears. So phi of 0 is the coefficients. 2 minus 2 square root of 2, 2 plus 2 square root of 2, and 1 and 1. Now, phi 0 inverse, well, it's 1 over the determinant. Now that's going to be diagonal, which is 2 minus 2 root 2. Subtract the other diagonal, so minus 2 plus 2 root 2. And then, what do? Well, the rule is you swap those entries, 1 and 2 minus 2 root 2, and then you flip the signs, minus 1 and minus 2 plus 2 root 2. All right, so that's the inverse. Well, we should clean it up. And, okay, we can. Some nice things happen. For example, 2 minus 2. The 2's actually cancel. And so what do we end up with? Well, what we have is this is the same as 1 over, we have minus 4 times square root of 2. Yes, we do. Yeah, that's happening. And, okay, times everything else. 1 minus 2 plus 2 root 2. And minus 1, 2 minus 2 root 2. And, well, okay, you can move the minus up, but you can also multiply top and bottom by square root of 2. And so we end up with the same thing as minus square root of 2 over 8 times this part here. All right. right, so there's our phi 0 inverse. Now we're ready to find e to the at, because we're going to multiply phi of t by this. And we're going to see what we get. Okay, so so we'll copy this down. So 2 minus 2 root 2. E to the root 2 times t. E to the root 2 times t. 2 plus 2 root 2. E to the minus root 2 times t. E to the minus root 2 times t. Times minus root 2 over 8. Times 1 minus 1. Minus 2 plus 2 root 2. And 2 minus 2 root 2. And now let's just give ourselves a stretch. Pat ourselves on the back, say it's okay. We're going to make it. We're okay. All right. Good. I'm glad we gave ourselves a little pep talk, because we probably need it going to finish the rest of this problem. All right. So, the constant comes out to the front. We can just not worry about it till we need to. So minus root 2 over 8. And so what do we have? We have 2 minus 2 root 2 e to the root 2t subtract 2 plus 2 root 2 e to the minus root 2t. Okay, this minus that. Yeah. That's just one entry. That's one single entry. Okay, so this minus that. And then what do we have? Well, we have 2 minus 2 root 2, 2 plus 2 root 2. So let's actually do that computation here up to the side. So 2 minus 2 root 2 and 2 plus 2 root 2. And if you look, it's like a minus b, a plus b. So that's be a squared, which is 4, minus b squared, which would be 8. So that's negative 4. So we have positive 4, because there's a negative that we didn't take into account. So we have 4 e to the root 2 times t. And then here, well, it's the same computation. And then so it's minus 4 e to the minus root 2 times t. All right, well, that one wasn't so bad. And then what do we have? Well, we have e to the root 2 times t subtract e to the minus root 2 times t. Okay, that one wasn't so bad. Doom, doom. And then we get minus 2 plus 2 root 2 e to the root 2t. And then plus 2 minus 2 root 2 e to the minus root 2t. And what do we do here? This is fun. This is fun. Now we sort of pause for a second and say, have we made any mistakes? And you notice there's a very long pause going on here. And the reason there's a very long pause is this is not quite giving what it needs to give. And so what I'm trying to figure out is where I've made a mistake. Now, in case you're wondering why I say it's not quite giving what needs to happen, is I'm thinking about what happens when you plug in time t equals 0. You should get the identity matrix. So you get zeros in these corners, which that's a good thing. When you plug 0 into here, you'll see that the 2's cancel. You get minus 4 times square root of 2. And then the question is, if I multiply that by minus square root of 2 over 8, does that equal 1? And it does. Okay, so we're good. It does work out. All right, so good news. This is phi of t. Okay. Oops, sorry, not phi of t. This is e to the at. We did it. So, remember, we had to find the exponential matrix, and that's what it is. That's the exponential matrix. Whew. Oh my gosh. Oh my gosh. Ooh. Oh, wow. Okay. All right. You're doing great. You're doing great. You know, positive affirmations. Remember, we love ourselves. You're doing great. You did such a good job. You deserve this. Okay. Are we done? No. What's left to be done? Solve for x0. Okay. We're told x of 0 is 2, 2. All right. Grab some blank paper because we're running out of space. And now, the key thing is, once you have e to the at, we have that x of t is equal to e to the at times x0. All right, well, we have e of at, and we have x0 is 2, 2. So we get, we copy this down, minus square root of 2 over 8 times this whole expression. 2 minus 2 root 2 e to the root 2t minus 2 plus 2 root 2 e to the minus root 2t e to the root 2t minus e to the minus root 2t 4 e to the root 2t minus 4 e to the minus root 2t minus 2 plus 2 root 2 e to the root 2t plus 2 minus 2 root 2 e to the minus root 2t times 2, 2. Okay, so that's our x0. So once we carry out this computation, we will be done with this problem. All right, so what do we have? Well, notice I can pull out a factor of 2 here and just say, think of this as 1, 1, but I'll pull a factor of 2 out. So this is minus square root of 2 over 4, so I'm bringing out a factor of 2. And then I'm just going to multiply by 1, 1. So it's this 1, 1, 1, 1. So I'm just going to add. Okay, so we're doing this plus this. So notice here, we're going to get 6 minus 2 root 2 e to the root 2t, because that's 2 and 4. And then minus 6 plus 2 root 2 e to the minus root 2t. So again, I'm just 1, 1 just means add the two terms together. So I'm adding them together. All right. Great. Wonderful. Wonderful. Okay. And now do the same thing down here. So we're going to add the terms together. Now I have a plus 1 here. I see a minus 2. Now when I bring this in, if I have 1 minus 2, really it's going to become minus 1. So minus 1 plus 2 root 2 e to the root 2t, and then plus 1 minus 2 root 2 e to the minus root 2t. Done. Done. Okay. It's possible to do these problems, but again, I'm just going to tell you, we are not going to ask a problem like this on the exam. We are not going to do that to you. We like you way too much. Oh, my goodness. Oh, my goodness. Wow. Wow, wow, wow. 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 Okay. Wow. Okay, number 6. All right. Oh, Laplace transform. Oh, woohoo! We made it out of systems. And so I went and I made sure I had my table of Laplace transforms ready to go. Okay, so part A. Write the following function using the unit step function and find its Laplace transform. All right. Now, the nice thing about the unit step function is you just need to know when do you actually do your step. In other words, when do you transition? And the key here is we change our behavior at pi. All right, so first step is we write the function using the unit step function. So you say, okay, what's your initial behavior? In other words, at time starting at 0, how does it behave? And the answer is it behaves like 1. Then you say, okay, when does it change behavior? You say, well, it changes behavior at time t minus, at time pi. So you put a u of t minus pi. That's just a way of saying, we're changing behavior. And now what you do is you turn off what it was doing before pi. It was doing 1, so you subtract 1. You turn on what it will do starting from time pi, and so plus t e to the t minus pi. All right, great. That's basically it for the right, but we're going to write a little bit more. And the key here is whatever is multiplied by a unit step function, t minus, say in our case, t minus pi, everything where I see attached to it, the t should look like t minus pi. Notice this t does not. This t minus pi, that looks great. This t, not so much. Not feeling it. So we're going to fix it. All right, so this is really 1 plus u t minus pi times minus 1 plus, now this t is t minus pi plus pi. Add and subtract e to the t minus pi. Or, if you like, that's 1 plus our unit step function, t minus pi, negative 1 plus t minus pi e to the t minus pi plus pi e to the t minus pi. All right, so there we go. Now, find the Laplace transform. Okay, so from here, it's not so bad. Whoops. If I can do the Laplace symbol right. So Laplace transform of the function. We just go through it step by step. So 1, that should be number 1 on the list, and it is. 1 goes to 1 over s. You're like, oh, is 2 not the second thing on the list? No, nothing that silly. So 1 over s. Now, this u of t minus pi, because we've set everything up, so everything attached here looks like f of t minus a. So that says, okay, you're going to have an e to the minus pi s. So we have an e to the minus pi s. And then we go through and we just transfer each piece. So, for example, minus 1 is the same as minus, just what would happen with 1. So that's minus 1 over s. T minus pi, e to the t minus pi. Now, because we've taken care of the shift, we're looking for t e to the t. Well, that's here. So that'd be 1 over s minus 1 squared. squared. So plus 1 over s minus 1 squared. Then your pi, now again, this e to the t minus pi, you think of it as e to the t, and that's on our list. So that's going to be 1 over s minus 1. So pi 1 over s minus 1. And that's it. We're done. We wrote it, and we found the Laplace transform. Great, great. Beautiful. All right, part B. Find the inverse Laplace transform for the following function. And 5 e to the minus pi s times s over s plus 2 squared plus 25. All right, great. Well, can we do it? Is it possible? Yeah, it's possible. It's very possible. Notice there's the e to the minus pi s. So I'm going to put that to the side. So I think this is 5s over s plus 2 quantity squared plus 25 e to the minus pi s. And this e to the minus pi s on the end is signaling, hey, you know what? There's going to be a shift in our final answer. So we're going to be ready for that. Now the question is, how about this first part? 5s over s plus 2 squared plus 25. So we start looking for it. So we have s plus 2 squared. Well, let's see. What do we have? S plus 2 squared plus 25. That looks a lot like what we see here. So minus s plus 2, that's minus minus 2. That's no problem. 25 is 5 squared. But there's a catch. It's not exactly right, right? See that 5s? We would like there to be s minus a. We don't have that. So we say, okay, let's get to that point. So the way we get there is we find a way to rewrite the expression. So the denominator, again, just to emphasize where we're going here, it's s minus minus 2 squared plus 25, 5 squared. And we have our shift on this side here. So we have s minus a squared plus k squared. So you really would like minus a upstairs. So we're going to do what we often do, which is s minus minus a. And then we say, okay, so that's really like s plus 2. But now we're like, oops, we've changed it. So we're going to compensate it by subtracting 2. And notice we've added 0. So let's break this into parts. And the parts we're going to break it into is there's this piece, and then there's this piece here. Okay, so what do we have? Well, we have the following. So we'll get, this is 5 s minus minus 2 over s minus minus 2 squared plus 5 squared. And that's e to the minus pi s. Now that's just the first part. Then there's this little extra piece here. So I'm going to subtract 2. And then I have 5 over s minus minus 2 squared plus 5 squared e to the minus pi s. Okay, and if we've done that, now we're actually pretty happy. We can see we have, all right, s minus a over s minus a squared plus k squared. And this one, look what we have. We have k over s minus a squared plus k squared, which means these parts are now on our table. And that's the goal. When we're doing inverse Laplace transform, it's make it look like something on your table. So this first one is going to look like an e to the at cosine kt, and the second one will look like e to the at sine kt. So let's be careful here. And this part by itself, just that part alone, So a equals minus 2, k equals 5. So this would be e to the minus 2t. We're in this one. So that's the cosine 5t. And this part, again, just this part here, that's the part that matches with the e to the at sine kt. So e to the minus 2t sine of 5t. All right, so are we ready? What's our final answer going to look like? Well, the thing is, we have to shift. So our final answer, well, they both shift at pi. So we're going to have a u t minus pi, that's part of our answer, times. There's a factor of 5, so we're going to have 5. And don't forget, these shift by pi as well. So e to minus 2 t minus pi cosine of 5 t minus pi. Okay, so that's the first one. Minus 2, so because there's a minus 2 e to the minus 2 t minus pi, and then sine of 5 t minus pi. And we're done. We don't have to simplify. Be a little bit careful here. So sine of 5t minus 5 pi. Minus 5 pi is not exactly back to where you started. You would actually go once, twice, and a half. So it's not the same as sine of 5t. It would be the negative sine of 5t. Same thing here. It would be negative cosine of 5t. It's probably better just to leave it as is. Whew, wow. This is so strange. A problem that we fit on a page? That seems so normal. Well, okay. It happens sometimes. It happens sometimes. All right. Well, that brings us to number 7. Okay. A large group of people marched in cadence. So think of it as, bum, bum, bum. They're all marching. Doo, 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 doo. Sometimes you see these people doing drills. Marching band. Doo, 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 doo. They all march at the same pace. And okay, so they're marching in cadence when crossing a bridge. The mechanical vibration of the bridge is governed by the following equation. Y double prime plus 9y is the sum, k equals 1 to infinity, delta t minus k, where y of 0 equals 0 and y prime of 0 equals 0. Okay, and y of t denotes the displacement of the bridge from equilibrium at time t. Delta t minus k represents the external force applied by the people together to the bridge at time t equals k. So in other words, at time t equals k, there's like it's like they're all stepping at the same point. Boom, boom, boom. So there's this pulse. Boom, boom, boom. And so that's what's happening here. There's this nice little pulse. Remember that delta represents the delta function. Okay, so that's the whole setup. We haven't done anything. There's no question yet. Now we get to the question. Solve the above initial value problem using the method of Laplace transform and explain why such a march can be damaging to the bridge as t becomes large. Okay, so let's start with the first part of this question. Solving the initial value problem using the method of Laplace transform. We should anticipate this kind of a question. And the nice thing is our initial conditions, 0 and 0, great. And so we only have the thing is the y double prime. But notice second derivative says s squared times the transform of just the function. The x0, x prime is 0, just replace x's by y's. Those parts go away. Wonderful. So what we have is, we'll do this write it in slow motion. Laplace y double prime plus 9, Laplace y. And, well, we'll bring sum k equals 1 to infinity, and we'll do the Laplace transform of delta t minus k. All right. So, Laplace of y double prime, that is, as we just pointed to the page, this is going to be s squared y of s. Plus 9, Laplace of y is y of s. Equals the sum 1 to infinity. And Laplace of delta t minus k, well, the nice thing is, it's on our sheet. Delta t minus a is e to the minus as, so it becomes e to the minus ks. All right, e to the minus k times s. Okay, well, not too hard to figure out what happens here. So we have y of s times s squared plus 9, and that's the sum, k equals 1 to infinity, e to the minus ks. So we get that y of s is equal to sum, k equals 1 to infinity, of, well, all right, this is 1 over s squared plus 9, e to the minus ks. And now we say, okay, well, this is good. This is good. We're close, right? So 1 over s squared plus 9, does that look like something? Well, it looks a lot like the sign. Think of a equals 3. You got an s squared plus 9 downstairs. We just need a 3 upstairs. Well, that's okay. We have the technology to make that a 3 upstairs. We'll make that a 3, make that a 1/3. No problem. And then we're like, well, great. This part right here would be sine of 3t. Well, what about the other piece? Well, the e to the minus ks, that says, oops, there's a shift going on. And now, like, okay, well, that's wonderful. So we can do the inverse Laplace of each little piece. So what we end up with is now, inverse Laplace, we say that y of t will be equal to, well, the sum, k equals 1 to infinity of 1/3, and then it's the sine of 3t, except there's been a shift, so sine of 3, and here it's shifted to k, so t minus k, and then don't forget there's also a unit step function of t minus k. All right, there's the answer. Okay, well, that wasn't so bad. Then there's this interesting part. It says, and explain why such a march can be damaging to the bridge as t becomes large. All right, what do you think is happening here as t becomes large? Well, as t gets larger, we have more of these sine functions compiling and adding in. So initially at time 0, nothing's turned on. Nothing's happened to the bridge. At time 1, there's like a foot that hits the bridge. At time 2, there's a second foot. Time 3, there's another one. And so you have all this repeated action hitting the bridge. Here's the thing. It says, explain why such a march can be damaging. It turns out this march is not damaging. And you won't have any problem with what's going on here. Now, I want to say you have to be careful. And so let me explain a little bit here. There's some interesting things that go on. It does happen that historically this has been the case when they had troops march across bridges, that bridges would start to crumble and break. That's actually true. It's happened. And the reason that it happens is because everybody's hitting at the exact same time. You can create harmonics, where what you have is things sort of build on each other. So if you can imagine, like, if you've ever been on a swing before, and you're pushing at just the right time to increase your height, but you keep doing that over and over, and next thing you know, you're actually going crazy on that swing, and it's very scary, or thrilling, depending upon your level of adrenaline needs. But what you need to do to have that happen is you need to have it hitting at just the right time. Because troops would march in cadence, if they happen to have the cadence matched with the natural oscillation, then you'd have this sort of reinforcing, where what happens is initially you have a small bump, becomes like a bigger bump, becomes a bigger bump, where in other words, they're stacking on top of each other, and there's no cancellation. So the way that they learned to deal with it is that when they would get to the bridge, they would deliberately break cadence, so that when you crossed, you want to have people stacking on top of each other. You'd have, instead of having the signs stack one on top, you'd have them offset slightly. And because of their offset, they're out of phase, what happens is you might have one thing helping you pull up, but the other one helps you pull down. And so the key here is that our steps are out of phase on this particular cadence. So they're not building up, they're actually canceling out. And so you never get anything very wild. This is a perfectly fine. We would never have any problems for this walk. Now, what could have been bad? Now, what could have been bad is we could have had the following situation, and namely, if let's suppose this had not been delta t minus k, this has been delta t minus 2 times k times pi. Then what would have happened is that the signs would have stacked. Everything would have been in phase, and so you'd have had a greater and greater force building up, or I should say greater and greater displacement, and the bridge would have totally collapsed. Here, no problem. In fact, it barely notices it at all. So that's be careful. And so that's what's going on. It's an interesting idea. Now, there's a beautiful thought experiment. I would say on a test, this sort of philosophical statement, it's a little bit more than what we would expect you to do. We're not a philosophy class. This is not a physics class. We're not asking for essays. If we ever ask for any explanation, like one sentence is what we're looking for. One sentence. Nothing more, nothing less. That's it with Laplace, but not it with the problems. One last problem. Okay, so let's bring it home. Number 8. Okay, so find the recurrence relation for the coefficients of the series solution around x equals 0 for the following equation, and form the series solution to the equation with the first 7 terms. All right, 7. In other words, we go up until x to the 6 with C0 and C1 as 2 constants. So we're C0 and C1. Those are our initial conditions, and here they're not giving the initial conditions. So that's okay. We're just arbitrary. All right, so y double prime minus xy prime minus y equals 0. Now this should be something we should be very comfortable with. Now the nice thing is, whenever we see series solutions problems, and you're dealing with a series solutions problem when it uses the phrase series solution, that's a really big clue that we're doing something that involves series solutions. The nice thing about it is that the first part of it is very mechanical, automatic. Not a lot of thought has to go into it. And by that I mean we say our answer has a very particular form. So sum 0 to infinity, c sub k, x to the k, y prime, well, sum 0 to infinity, k, c sub k, x to the k minus 1, y double prime. So you might notice I'm not even really thinking right now. You can tell I'm not thinking because I'm saying things while I'm writing other things down. It's like, how can that be possible? How can you say something while writing something else down? Well, because there's no thought process. We know what y prime, and y double prime are automatically. We just write them down. Okay. Then what we do is we plug them in. What we mean by that is that this y will come in for y. This y prime will come in for y prime. This y double prime will come in for y double prime. So we're going to substitute these expressions into our differential equation. And again, this is a point where we don't need a lot of thought going on at this stage. So we have y double prime sum. Oops. Let's try and write our sums in a nice legible way. 0 to infinity, k minus 1, ck, x to the k minus 2. Okay, minus x and y prime, sum, k equals 0 to infinity, k, ck, x to the k minus 1, minus y, all right, that's the sum, k equals 0 to infinity, ck, x to the k, and all that equals 0. All right, great. Well, good. This is the stage where thought comes into play. And so the thought here is putting things into one sum. So there's a couple things we want to do. Bring in the coefficients, and then we want to shift the indexes, or call that substitution, and then we want to pull off first terms as needed. And then we can put everything into one big sum. Okay, so as far as coefficients go, there aren't many things we have to do. There's a little bit. We got to account for this x. Okay, so it's going to come in. Other than that, not much we have to do. So let's update our formula. So we've pulled in our coefficients. We sub the sums. So sum k equals 0 to infinity. K minus 1, ck x to the k minus 2, minus sum. Now when you bring this in, this will become k ck x to the k, minus the sum, k equals 0 to infinity, ck x to the k. All right, well, we want all the powers to match. And so we're going to go through and say, let's just shift our indexes so the powers line up. And we say, okay, well, let's make all of them equal to the same. So we'll just say k equals L. So everything, it comes to the power L. So x to the k, okay, so k equals L. X to the k, all right, k equals L. X to the k minus 2, all right, k minus 2 equals L. All right, so we're just going to do a shift. Now the last two, they're just going to copy these same things down again, except instead of k, we write L. So not a lot has to go on. The first one, there's some stuff that has to go on. So k minus 2 equals L, or if you like, L equals k plus 2. So we can work our way through it. All right, so let's start here with our sum. Where do we begin? Now, this is the same as the sum, L equals, and when k equals 0, 0 minus 2 would be minus 2. And then we have k, which is, not L equals k plus 2, k equals L plus 2. That's what we mean. Gosh, I can't believe I copied that down wrong. L plus 2, L plus 1, C, L plus 2, x to the L. And these other sums are very quick to write. L, C, L, x to the L, sum L equals 0 to infinity, CL, x to the L. Now, we've got the powers matching, our coefficients are inside. The other thing is, where do we start? We start 0, 0, and minus 2. Minus 2? But wait a second. If you plug in minus 2, what do you see? 0. Right? Because L plus 2. Plug in minus 1, what do you see? 0. Okay. So, we can say, hey, we can change that to 0. Now, what we've actually done is we've pulled the first two terms off. And when we pulled the first two terms off, they were both 0. If they hadn't been 0, we would still pull the first couple terms off. So the ability to pull terms off as needed is something that we want to be comfortable doing. And it certainly works here. So we say, all right, well, great. So now we can put everything into one sum. So we have that the sum from L equals 0 to infinity of L plus 2 times L plus 1 times C L plus 2. That's the first coefficients. I'm just grabbing the coefficients of x to the L. There's going to be an x to the L on the end here. Minus L CL minus CL. All that times x to the L equals 0. Okay, great. Now, we're out of space. That's all right. You can just grab a blank piece of paper, right? Yeah. Keep going. Keep going. Okay, so what do we have here? Well, the key is just to say this part right here, this coefficient, has to equal 0. Why? Well, because these are the coefficients of powers of x. And if we look at the coefficient for powers of x over here, they equal 0. Now you might say, well, wait, why did we have to wait all the way to here to say this part equals 0? Why don't we just start with like this equals 0 or that equals 0? Well, the problem is there's powers of x that are repeated in these three different pieces. So until we put them all together, we can't pull out our equals 0 trump card. But now we can. All right, so here we go. So we have that L plus 2 times L plus 1 times C sub L plus 2. Now notice these both are CL, so I can pull that out. So there's really L plus 1, CL equals 0, and this is for L greater than or equal to 0. All right. Now this is a really important relationship. Now we can do some things to help clean it up. Notice I can, for instance, the L plus 1 is common, and since L starts at 0, L plus 1 will never be 0, so we can divide out. And so what we end up with is the following relationship. C L plus 2 is equal to 1 over L plus 2 C sub L. Now, this is for L greater than or equal to 0. And this right here, we should pause. And this is an important part. I'm boxing it not because it's part of the answer, but just because it's so important. We should really pause and say, hey, this is our recurrence relationship. And oftentimes, this will be an important part of finding the answer. Yeah, this is like the most important part of series solutions, is saying, hey, there's a recurrence relationship, and we've just found it. Now, I personally like to rewrite it so I can talk about this coefficient as my C sub n. So do a quick change. We'll call L plus 2 n. So we get Cn is 1 over n. And this L, well, L is n minus 2. So Cn minus 2. And, well, I start at L equals 0, so that means I start, sorry, not for L, I start n at 2. So this is also the recurrence relationship. It's the same thing, just a different name. And the ability to change names is a really cool idea and a very powerful one in mathematics. And the sooner you recognize that and you're able to do that, the better. Okay, so now, with all that work, what do we have? Oh, we did need to find the recurrence relationship. Good, so we did it. So, woohoo, good for us. Good job, us. All right. And now form the series solutions to the equation with the first 7 terms until the term x to the 6, c0, and c1 as 2 constants. All right. So here we go. So c0, c1, these are basically our free constants. Normally, these are the same thing as our initial conditions, because if you know what happens to the series solution at 0 and the derivative at 0, that determines your C1 and C0. Okay, so these are our initial conditions. All right, so now we need the rest. Well, what is C2? According to this, C2 is 1/2 C0. All right, great. Well, that's in terms of C0, so that's good enough. How about C3? Well, n equals 3. 1/3 C1. Okay, that's in terms of C0, C1. How about C4? So n equals 4. So that's 1/4 C2. Now I can't stop here because I have to get in terms of C0 and C1. But we know what C2 is. So we say, okay, C2 is 1/2 C0. So that would make this 1/8 C0. All right, well, how about C5? What would that be? Okay, C5, n equals 5, 1/5 C3. But we know what C3 is, so 1/5 times 1/3 is 1/15 C1. How about C6? Well, n equals 6, 1/6 C4. Well, what's C4? 1/8 times C0. So 1/6 times 1/8 makes 1/48 C0. And now what? We stop. Wait, what? Why? Okay, remember it said until the term for x to the 6. Well, what's the coefficient for x to the 6? That's C6. So once we hit C6, we've hit the first 7 terms. So we now have our answer. So our answer would be C0, our constant, C1 times x, plus C2, 1/2 C0 x squared. C3, 1/3 C1 x cubed. C4, 1/8 C0 x to the 4th. C5, 1/15 C1 x to the 5th. And C6, 1/48 C0 x to the 6th. So that's the answer for the first 7 terms. Everything expressed in terms of C0 and C1. All right. Well, there were some tough ones on this practice. And if you made it, good for you. And if you didn't, don't get stressed. Don't get stressed. The practice exam questions are not quite as vetted as the actual exam questions are. So you'll be fine. Keep studying. You'll do wonderful. We believe in you. And, well, maybe see you again. Bye.